Assalamualaikum and hi. In this video, we are going to share about our project under Fluid Mechanics courses, which is a pipe network analysis. The pipe network shall be analyzed for the determination of the nodal pressure, heads, and the connection discharge. The network is analyzed for the worst combination of discharge withdrawals, which might result in low pressure heads in certain areas. The water distribution network have three types of configuration. The first one is branch or tree-like configuration, and the second one is loop configuration, and the last one is branch and loop configuration. There are three methods we use to solve for pipe network in loop configuration, which is the first one is Hardy-Cross using either Darcy-Weisbach or Hazen-Williams. The second one is linear theory, and the third one is Newton-Raphson. In this project, we choose Hardy-Cross method by using Darcy-Weisbach equation.
After settle, calculate the head loss coefficient K for each pipe in each loop 1, 2, 3 and 6. So we're gonna continue thus by calculate the correction, and we should to reach for at least 2 loops to get value 0.000 something. So here are our final correction value for the first trial. In the loop 1 we get negative 0.0084. In the loop 2, we got 0.0037. In the loop 3, we get negative 0.0109. In the loop 6, we get negative 0.00531. Since we not reach the correction for at least 2 loops to get value 0.000 something, so we need to continue for the second trial.
So we continue with second trial for loop 1, 2, 3 and 6, but we still use the same pipe as before and the head loss coefficient too, but we change the assumed discharge so that we can get a different head loss value and the correction value. So the calculation is like this. So after we change the value of assumed discharge, we got another value for the correction, and for the first loop we got the value is negative 0.0102. For the second loop, we got negative 0.14, and for the third loop, we got negative 0.001, and the sixth loop, we got negative 0.0127. So since we still did not reach the at least 2 loop for value 0.000 something, we continue for third trial.
So in the second trial, we still didn't reach the target for the correction value. So we continue to third trial, and we still use the same methods as in second trial, which we are using the same pipe and the same value of head loss coefficient. But we change the value of the assumed discharge. By that, we can get the different value for the head loss and the correction value. So here is the calculation. The correction value that we get in the third trial for loop 1 is 0.0104, loop 2 negative 0.025, loop 3 negative 0.015, and the last one, loop 6, is negative 0.0064. So as we can see in the third trial also, we didn't get the value for the correction, which is 2 decimal number, which is 0.000 something. So we continue with the fourth trial.
So we continue with fourth trial for loop 1, 2, 3 and 6. We use the same head loss coefficient, but we change the assumed discharge. So for the fourth trial, this is the loops. So for the fourth trial, the correction for loop 1 is negative 0.0155 and for loop 2 is negative 0.0005. 484. The correction for loop 3 is negative 0.004 and for loop 6 is negative 0.003999. So for this fourth trial, we just got one correction that achieved 0.000xx. So we continue for the next trial.
So in this fifth trial, we still use same pipe direction and same schematic pipe as before, but we just change their assumed discharge for each pipe in each loop 1, 2, 3 and 6. So here are the results. Here are our final correction value for fifth trial. For loop 1, we get negative 0.00054. For the loop 2, we got 0.071. For the loop 3, we got negative 0.007. For the loop 6, we got negative 0.000508. So basically, fifth trial is our final trial because we already reached the value 0.00 something for at least 2 loops.
So the conclusion is the distribution system is a network of pipelines which distribute water to consumers. They are designed to adequately meet the water requirements for a combination of domestic, commercial, industrial and firefighting users. In any pipe network, the algebraic sum of the pressure drops around the closed loop must be zero, which is there can be no discontinuity of pressure, as well as the flow entering the junction must be equal to the flow leaving that junction. For example, the law of continuity must be complied with.